What I'd like to do now is to continue to apply Newton's second law the way we have been doing, to look at a physical system, to draw free body diagrams for the objects of interest, to write the equations of motion, and to interpret what those equations of motion mean. But for the very first time in our lecture series here, I'm going to describe what I refer to as an essential. As we go along through the lecture series, periodically I'll say, this is essential, and I'll make some very fundamental argument of our physics. The reason why I'm doing this is that I've come to understand after years of studying physics is that you cannot be successful until you have the skill of making the kinds of arguments that you see me make up here at the board day in and day out. You need to spend some time with Newton's second law performing the calculations, making the reasonable arguments on your own. It's quite a simple thing to sit in the audience and watch me do it and say, yes, that makes sense, that seems to be true, okay, I follow that. When you're just watching it as an audience member. Because you're not the one who actually has to do it and think the things up. It's a much more difficult thing to face a blank page and work out an argument all on your own. However, if you do that continuously and are able to make these arguments and start from scratch, you will find yourself getting better at physics. You might make an argument, well, Shiley, I'll only know how to do these set of things that you've called out. I'll know how to do those, but other things I won't be able to do. Well, that's not true. It's not the goal. The goal of essentials is that you'll gain practice at making rational arguments in general, that you'll develop it as a skill. And what you will find, I promise you, is that later on you'll be able to make your own arguments in situations that are not things that you have memorized, that there are not things that I've talked about, but you've developed the skill of making rational arguments on your own, and that is certainly a very valuable thing. So here is the first of the essentials. And later on, after this lecture is over and we've all gone home, you should, in principle, take out a piece of paper and see if you can make this argument right off the top of your head. If you find yourself getting stuck at some point, then by all means, peek at your notes and see what you've done wrong and then proceed from there. But in principle, everybody should be able to make this argument. Here we're going to describe a thing known as Atwood's machine. And to us, it's a new physical system to describe. We just talked about the cart and the horse, but surely this is different. Surely this takes a different application of Newton's laws in order to understand this. Not true. I'm going to follow the same procedure that I did before. I'm going to draw a diagram of the system. I'm going to have a little discussion about what it is that I'm talking about. And then I'm going to draw a free body diagram so that I can understand the nature of the forces that act in their directions. And then I'll apply Newton's second law very judiciously to those free body diagrams. I won't cheat at all. I won't make anything up. And then I'll write Newton's second law equation based on those free body diagrams to get my equations of motion, and then I'll proceed from there. So that's what I'm doing sort of procedurally and learning how to solve problems. So Atwood's machine is a pulley which for our purposes at the moment is massless and frictionless. That is going to make the analysis here easier. So it's an assumption that I'm making. We have to make this discussion about, what are the details of the system that I'm solving. Don't worry that that's not very realistic, because later on in our physics, we will make the pulley massive and frictional. And so we'll be able to solve that problem later on, but perhaps we'll walk before we can run. So here I have a massless, frictionless pulley. Massless means it takes no force whatsoever to turn it. It turns so easily as if it were not even there. And there's no friction force, say, in the axle of the pulley, and therefore there's nothing that prevents the pulley from turning. And so here you see I have a mass M1 on the left-hand side of the pulley here, and it has a rope attached to it which goes over the pulley, and it's attached to another mass M2. And so I'm making a condition here that M1 is greater than M2. I'm telling you that that's true. It's not necessarily true. In fact, I could create the situation where M1 and M2 are in fact equal to each other, but it's not terribly interesting. You would find that if you went into the laboratory and built that with M1 and M2 equal to each other, and you let it go, that it wouldn't move at all. It would be rather uninteresting circumstance. So I have M1 greater than M2, so what I expect is that M1, when I release it, M1 having the greater weight. This is just my expectation of having lived and seeing how the universe works. I haven't done any calculations yet. I can't prove this. But my expectation is that M1 will fall and M2 will rise. When M1 falls, M2 has to rise because they are connected by an inextensible cord over the pulley. I'm not saying the word inextensible lightly. What I mean is that the cord is not stretchy. That's important. because it gives me a little advantage in solving the problem in the following way. If mass 1 descends 1 meter, that's a little bit ridiculous based on the scale of things and the way that it looks, but certainly I can imagine a situation that M1 falls 1 meter. Because the cable is inextensible and has a finite length, that means that 2 must raise 1 meter. What I conclude from that is that their displacements are equal. You might look at it, well, they're not exactly equal because displacement is a vector, and 1 displaces downward and 2 displaces upward. So technically not the same because the directions are not the same. In order for 2 vector displacements to be equal, they must have the same direction. Well, I have an answer to that and a little bit of instruction, and that it's okay for me to choose coordinate systems differently for separate objects. I know that when objects have the same acceleration, I can treat them as one object. But I also know that in this analysis, I'm not going to do that. I'm going to treat 1 and 2 as if they're separate objects, which means I can make separate coordinate choices. So for M1, let me choose downward to be the positive direction, and therefore when 1 descends, that is a positive displacement. And for 2, let me choose upward to be the positive direction so that when it displaces upward, it has a positive displacement. Now under those conditions, when 1 goes down 1 meter and 2 goes up 1 meter, their displacements are equal. This displacement of 1 downward and 2 upward happens in a certain amount of time. It happens in the same amount of time. So if I were to describe the velocities of 1 and 2, I would realize that the displacement divided by the time was equal for the two, which means they have equal velocities as they rise and fall. If they have equal velocities, but those velocities then change as a function of time, they must change by the same amount, and so they have equal accelerations. So the fact that they're connected by an inextensible cord has a consequence that the displacement, velocity, and acceleration are the same for most mass M1 and M2, and I'm going to take advantage of that in my analysis. Certainly, you might like to connect them together with a rubber band and solve that problem. That problem, of course, is very sophisticated but completely solvable. Very sophisticated but completely solvable. But I would have to, it would just be more complicated in the mathematical expression of it. The technique of applying Newton's second law would be the same. I guess it's a big part of this lecture is what I'm impressing upon you is that no matter what the physical situation, the approach is the same. I just have to be really careful in my analysis. So here, that's the situation that I'm looking at. Atwood's machine, 1 descends, 2 rises, M1 is greater than M2. And now that I have an understanding of the system, I've had a discussion about it, I've looked at it, now I'm going to draw free body diagrams. I will draw a free body diagram for 1, and I will draw a free body diagram for 2. So here I go, drawing 1 out of its context, a box that represents 1. And I'll make a note here that the positive direction is downward for 1, that I made that choice. That's not a very common thing for me to do in a Newton's law sort of analysis, to draw that coordinate there. But because it's an issue of this problem, I'm going to just make a special note there. Running down my list of forces, there are very few acting here because, in fact, there's only the weight of 1, M1G, acting downward, and the tension, T1, directed upward. There are no other forces acting. 1 is just dangling from a string, so there's no normal forces. In the absence of those normal forces, there's no friction forces. And so it turns out to be quite a simple system indeed, with just the 2 forces acting. I could draw a free body diagram for 2, so I draw a box labeled 2. Again, I'll label the direction of the coordinate system, lest I forget, which is directed upward for 2, so that they have the same acceleration, same velocity, same displacement. So for 2, again, I have the weight M2G acting downward and the tension T2 acting upward. I have some interest in these tensions T1 and T2, because looking at my diagram, I realize that why would 1 have a tension acting upward on it? Well, there's a rope there, yes, but where does the tension, why is it not slack? It's not slack because on the other end of the pulley is 2. It is 2 that exerts a force on 1 the same way that our horse exerted a force on the cart. And the tension T2 that acts on object 2 is caused by 1, in the same way that the force on the horse acting backward was caused by the cart. They are an action-reaction pair. And a consequence of that is that T1 is equal to T2, and so I'm going to call both of them T in my analysis. And I'm very happy to do that because it means I'm reducing the number of variables that appear. And that certainly is very helpful. It will greatly simplify my algebra and give me a pleasing result. So here are my free body diagrams. Now that I've done that, it's time for me to do a Newton's second law analysis. So I'll begin with Newton's second law applied to object 1. Sigma F is equal to ma. On the left-hand side, I'm using my free body diagram to give me an idea about the sum of the forces that act in this situation. So looking at my free body diagram for 1 and realizing that downward is the positive direction, m1g is a positive force, and T, here T1 on the diagram, but now I'm going to call it T because I know it's all the same tension. T is a negative force. And I described earlier my habit of leading my algebra, trying not to have leading negative signs. So I'll start when I write the sum of the forces, is the sum of the forces acting on object 1 is the positive weight force, m1g, plus the negative tension. So it's minus T in the sum of the forces. That must be equal to m1. Being very careful, this equation of motion that I'm developing here describes block 1. So I must write m1 there multiplied by a. And that is the equation of motion. So I put a box around that because that is the equation that describes the motion of object 1, no matter what the state of motion is. It's a very valuable thing. Now applying Newton's second law to object number 2, sigma F is equal to ma, I'm searching for the left-hand side, the sum of the forces. Look at this diagram and recall now that upward is positive. So on the free body diagram for 2, it's T that is the positive force, and it's m2 times g, the weight acting downward, which is the negative force. So I write my Newton's second law equation accordingly here on the left-hand side. The positive tension plus the negative weight. And so it's tension minus m2g is equal to m2, because this is the equation of motion for mass 2. It's appropriate for me to use m2 there, is equal to a. Notice that in my first equation of motion and my second equation of motion, the accelerations are the same. Well, I've already made that argument. I've already made the argument that 1 and 2 are going to have the same acceleration according to the conditions that I set on my physical system here. So now I've considered my physical system and talked about it and described, how the details of it go and what the assumptions are and everything. I've drawn free body diagrams for the objects in question, and I've written Newton's second law to get equations of motion. Now all that's left is the analysis. And to a certain extent, the analysis it depends on what I want to know. Well, what I want to know for my purposes here is what is the acceleration. Notice that the tension in the cable is also unknown. I could ask the question, what is the tension? I could go searching for it. But just for the practice of this particular example, I want to find out what the acceleration is. So to find the acceleration, I have to look to my equations of motion. Well, look here. My first equation has the unknown acceleration in it. Well, that's great. I can use this equation then, except that it has the unknown tension in it. My second equation also has the unknown acceleration I'm looking for, but it also has the unknown tension. So I have a situation here, an algebraic situation, where I have 2 equations and 2 unknowns. And we've all learned in our mathematical training that is all that is required in order to solve a system of equations is that I have the same number of unknowns as equations, or I can have some extra equations, so it makes things overdetermined. But in order to find or solve a system of 2 variables, I need at least 2 equations. Luckily, I have them. There are a lot of ways to proceed algebraically. You can do it differently if you like. Let me suggest a different way before I do my way. A way of solving these 2 equations for the acceleration would be to solve them both for t. And since they're both equal to t, they would have to be equal to each other, and then I could set the 2 equations next to each other and bang, t is eliminated, and then solve for the acceleration. It's not my style to do that. What I'll do instead is I'm going to take the second equation here and solve it for t, because it's convenient. All I have to do is take m2g and add it over to the other side of the equation, so I get t is equal to m2a plus m2g. I'll then take that equation for t, and I'll plug it into the first equation where t appears. I have to be careful, because here it's t is equal to m2a plus m2g, so these are both positive terms. I'm going to subtract both of those terms when I plug it into the first equation of motion. And so what I get is m1g minus m2a minus m2g is equal to m1a. Effectively eliminating t. T no longer appears in the equation, so I need not concern myself with what its value is. Now all I need to do in order to get to the answer that I want is to solve for the unknown variable a. To do that, I'll group all of the a's on the same side of the equation. So adding m2a over to the right-hand side, I have m1g minus m2g is equal to m1a plus m2a. Now, factoring out an a on the right-hand side and a g on the left-hand side, and solving, I get my result for the acceleration. Very pleasing result, which is part of the reason why I call this an essential, is because it's a beautiful problem to think about Newton's second law and also to think about the conclusions that I draw from it. Here the acceleration is equal to the ratio of the difference of the masses divided by the sum of the masses multiplied by g. A is equal to m1 minus m2 over m1 plus m2 multiplied by g. What does this mean? Well, I've made the assertion here that m1 is greater than m2. m1 is greater than m2, but surely the difference between m1 and m2, which is a positive quantity because m1 is larger, divided by the sum, this is a fraction, which means the acceleration of that system, the acceleration of 1 downward and the acceleration of A upward, will only be a fraction of g. Now, don't consider 2 for the moment. Consider 1. 1 is falling, and it falls, according to what I've derived here, with an acceleration that is only a fraction of g. And that makes sense, because if it was accelerating with an acceleration that was equal to or greater than g, that would be an acceleration greater than free fall. That you build this apparatus and it falls faster than it would if it was just gravity. No, I don't expect that, because I know that the tension pulling upward on 1 is going to retard its motion to a certain extent. And so, that makes an awful lot of sense, and it'd be a fraction of g. I'm curious. What would happen if I made m1 equal to m2, which at the start of the argument I said would be not an interesting thing to do? Well, now that I have my answer, I'm curious. If I make m1 equal to m2, then m1 minus m2 would be equal to 0, which means the whole thing goes to 0, which means the acceleration is 0, which is exactly what I expect. If I hang two masses on there, m1 and m2, and they're in fact equal to each other, the system will not accelerate. It'll just sit there. Don't forget, there are two states of motion for which the acceleration is equal to 0. If I built this in the laboratory and put m1 and m2 on there, and m1 and m2 are equal, it will sit there and not move at all. If I give it a nudge and give it a little initial velocity and get it will move with constant velocity. It will move with constant velocity because constant velocity satisfies the acceleration equal to 0. And that's a legitimate state of motion with the acceleration equal to 0. So there we have it, our first essential Atwood's machine, and what we've gotten out of this entire discussion, hopefully. And I'm going to reiterate, because I think it's the most important thing about this particular lecture, is that I draw my physical system and I contemplate the nature of it. I spend a little bit of time thinking about what the assumptions are, what I'm looking for in my solution. Then I draw free body diagrams for all objects that I have to in order to get where I'm going, and I apply Newton's second law to my free body diagrams. You know, people have said to me in introductory physics courses, I don't know where you're getting these equations from. I write a Newton's second law equation down, and I start solving things, and a hand goes up and says, I don't know, where are you getting these equations from? From the free body diagram. The free body diagram informs the left-hand side of Newton's second law to write an equation of motion. And then once I have those equations of motion, some problems I'll have one equation of motion, some problems I have 3 equations of motion, depending on how complicated it is, how many objects there are. But once I have those equations of motion, I know that I have a system of equations that describes every state of motion that the system can have, subject to the assumptions and approximations that I've made. And so then I just have to get busy doing the algebra to find answers to questions that I have. In this case, my question was, what is the acceleration of the system?